It's really started in 2021, the main. But our project, of course, the work started much earlier than that. So I'm going to give you a quick a kind of snapshot of what I'm trying to talk about here. Okay. So, when you experiment, right? You all do experiments. Do you want to maybe dim this frown? Does it do that or not?
Yeah, it does.
So I have 3 buttons there. Maybe 1 button in frown a little bit. Oh, this one, right? This was the most trouble. Oh, that's good. All right. So, when you experiment with observations and you develop a phenomenological laws, try to understand what it is, then you have models. Okay. After a while, you get a fundamental laws. And they get fundamental laws, you get new models, you do some calculation simulation. Then try to reproduce experiments. That's probably the major thing you want to do in all the science work, right? Okay. The question is that can we directly go from the I need to point here. You have to go from fundamentals to experiments. Of course, that's really from my point of view, that's what I'm trying to do. Let me look at this one. Okay, let's see. I can remove this one again. So that's what I try to do from a scientist point of view. I try to go film directly there without models. Okay. And then the idea we had since is that if you do experiments, you define the system, right? Do experiments, okay? And then you try to do these shoot lights, temperature, magnetic field, electric field, whatever. Then you do the measurements. And it turned out the very limited thing we can do for a system, we can do 3 things. You can put heat, or take heat out, or you can do work. There are a number of works we can do, 4 types actually, not many. And then you can change mass, eat food and sort of thing. And then you have the first law. That means everything you put in there will increase the energy of the system. Nothing more, nothing less. And however, when you do that one, the system will respond to it. You can do something. Okay. What it's doing that is going to produce entropy, basically. It's going to produce entropy. So when you produce entropy, what happens is that you can have driving force. Something drives that process. So when you drive that process, then you're going to say, okay, now, then after again experiments and so forth, we found the second law. Second law says that the system must produce entropy. So D is positive, D side is positive, time to get positive. Some simple, right? Of course, it takes many, many years to discover this. However, one problem is that the left side is equal, the right side is not equal. So that's been staying separate for a long time. Yeah. Until one great American decided to take a trip to Europe. Okay, so that's what happened in 1870s, 60s, up to 1950 years. That's why if you have not heard about it, it's a person called Gibbs. Okay, the Gibbs decided to go to Europe, do transfer learning. Yes. He has the large language model. He's an instructor at the Yale. And he decided maybe you get data points, right? Let's get more data points. So he went to Europe and then 1866, and they came back in December, and he came back in 1869. Not a very long time, right? 2.5 years, but that changed the world. He came back and he decided he did something, put the 2 together. Of course, in the inequality, you have to make it equal, put them together. So he said, let's say there's nothing happening in the system. Okay, no driving force. So he did that one. Then he made the first law. Then he started need to calculate entropy. That problem is 1873. That took him another about 40 years, 30 years. So in 1901, he got his statistics mechanics, and he passed away in 1903. It's good that he stayed long enough to get that invented. However, that invention was never published. Didn't time to publish it. Okay. And then, as you know, that probably in the 20s, we get quantum mechanics, Schrödinger equation. And then we get the statistical quantum mechanics, and then we talk about the density function theory. So this is another 40 years from 1920. And another way, of course, we remember we have this larger sign, right? Inequality. So that's always be seeing people working on. So it turned out it's so complex, they start a new branch called non-equilibrium. So you can see that it's the 1930s and the 70s, 80s, and so forth. But the three things are separate. The people study quantum mechanics, people study statistical mechanics, people study thermodynamics, all different people. They don't talk to each other. Okay. So then should be put together. Because means so let's how to do entropy. And I know you heard entropy before, right? Information entropy or Shannon entropy. Yeah. Quantum entropy actually started by experiment. You can measure it. You hit capacity integration, you get an entropy, 100%. However, how do you calculate? That's the key. And then the Gibbs, as he got the law, then he started how can you get the actual value? He invented statistical mechanics. Okay, this sentence is very important because he wrote that in his introduction. Today, even today, many people don't realize this the sentence he wrote. He said that imagine a great number of systems of the same nature. And it's the same, in the same mass, same volume, same temperature, whatever. But they're only different by configuration. That means they range differently a little bit. And maybe velocity, because I find temperature is motion. Right? That's it. Then put them together, you can get a problem. Then he said he could derive this equation, say entropy is equal to probability of different configurations, and you pick up a bigger. Of course, you know the Shannon equation. No, it's not. It's Gibbs equation, 1901. It's way before Shannon. Okay. But of course, that's okay because Shannon's different community, but the text and the things they reinvented. And 1901 is already discovered by Gibbs. So picking probability, right? Yeah. So that's actually, so I think we should not call Shannon, we should get a Gibbs entropy. Anyway, however, we use the Boltzmann too, right? Boltzmann entropy. Boltzmann entropy is a very special case, ideal case, in all the probability equal to the same. Then you got the Boltzmann entropy. Okay, so now see that you can, maybe I should add another term because Shannon entropy here. So I say Shannon is part of it. Right? Okay, so that means that you have the system, any system, same nature, but they have different configurations. Okay, configuration 1, 2, to all configuration you have. Okay, so that's entropy you have. However, the configurations are very important. What are the configurations? It means different arrangement, different velocity, and so forth. But each one could have entropy too, right? They're not zero entropy. But of course, it could zero entropy if you go to pure quantum configuration. But any configuration you have is not pure quantum configuration. Okay? So that means if you want to consider those of those configuration, you have to put them together, right? How can you do? You can calculate them by quantum mechanics. Yeah. And then put together now entropy two terms now. You have the information entropy, you have the quantum entropy. That makes sense? So two entropies, right? Information entropy and quantum entropy. That means if you only work on quantum, you get a part of entropy. If you only work on statistics, another part of entropy, right? But never the same entropy. That means Shannon entropy is incomplete. That's the conclusion, basically. So if you want to describe the all entropy of the system, you have to get both together. Okay, so that's called entropy. So basically, this partition function, you stack all the entropys up together. Okay. The word the term was not is newer of course. It didn't invented by me. I give a talk like you. It was on Zoom, so many people. We talk about our method. One postdoc said, "Oh, you should call it entropy." So, since 2021, we call it entropy now. Yeah. All right. So what is very critical is that if you only look at the statistics, like Shannon Gibbs entropy is incomplete. And if you only look at quantum mechanics, it's not complete. So that's the key. So that means if you want to describe the system completely, you must have both. Okay, that's what the machine is about. Okay, so if we can predict it, okay. If we cannot predict, we have to learn it. But if we only learn part of it, that's very incomplete. So you have to learn both of them at the same time. Okay, so quantum mechanics gives you just one slide. So it's showing the equation, which is about electrons and nuclei, and it's solved in the 1960s theoretically, and but the really solved was actually 1980s or 90s. You need both software and also the mathematical formula to solve it. But the key concept is that it's top of zero Kelvin. What it means that any system, doesn't matter what it is, at 0 Kelvin, you don't have one state, has lowest energy. Of course, it's very hard to say, what is my ground state? I don't know, right? I cannot go to 0 Kelvin. Okay, so you can do that. So that's its theory. And then you can calculate it. But if you think about if that configuration goes to high temperature, you can vibrate. You can do a lot of things, right? So you can calculate the entropy too. So you can two entropies. You can carry the electronic entropy or the photon entropy. Electron means the electrons start to redistribute. As soon as redistribution, that was the entropy you have, right? Peak log pk basically. So when you have distribution, even though distribution, zero, right? Log one is zero. But you have distribution, peak log pk, they give entropy. So you have electron, electron one, right? First, then you have the phonon, that's atom. You have the electron and nuclei, right? The electron vibrate and start to shift, you get entropy. And the atom start to shift, nuclei start to shift, you get entropy. You can predict them by quantum mechanics. If you know the atomic structures and whatever structure you have. So you can calculate it. And remember, this is only one configuration, right? But when the temperature increases, you get so many configurations. Just calculate all of them. So that's what statistical mechanics does that. Okay, I have all of them put them together, that's what you get. So that gives statistical mechanics says that entropy, free energy, and the partition function and probability. You can all calculate them. But now if you have now a quantum entropy, the entropy will be different. The only equation have to change, right? All the equation have to change. The change is very simple. It's only change from E to F. The relation between E and F. F is Hermann's energy. Is not the greatest German scientist. And E is total energy. And S is entropy. So put it together, the only change on the two sides is that you change from E to F. That's the only change. Everything else is identical. Okay? But of course, your probability is different now. Because each community has different entropy, the probability becomes different. The probability different, the difference of the probability becomes bigger and bigger when temperature goes higher. That's why you form liquid, right? It gets higher from the vapor. Okay, that's entropy driven. But now we can predict that one. However, these two actually go together if SK equals 0. That means each configuration has no entropy. Of course, they should be equal, right? So it's exactly going to be equal. So that's very good. So it reduced to the standard equation like before, but it's only for the pure quantum configuration. They have no any internal degree of freedom, so it's entropy equals 0. Make sense? Okay. So that means what is that entropy now? So entropy Z plus entropy. Z is the German word stands for the partition function. That's trauma. And the idea is that's where the term came from. A grad postdoc, Josh Robert. He said you should call it Zentropy, so we call it Zentropy now. In another paper, we credit him for creating the name. Okay, so also that's why I recorded. So if you go to recording at a 1 hour time, question answer phase, he mentioned she got Zentropy. So it's his contribution to the community. Okay, so then Penn wrote a very interesting kind called Zen. You see Zentropy, right? You can see it's Zen. This is like more philosophic, spiritual stuff. Okay, or that's probably what they try people's eyes for that. But I do want to mention that this paper talked about that already, 2016, and we have 2 books come up about the Zentropy. It's compiled papers where on this topic. All right, so to end is that to put it all together, this paper, if you want to read it, that paper just published this year, public review paper. Oh, there's somebody here. Okay, public review paper. Act of the 4 topics. It gives the equilibrium thermodynamics. Here there was my professor, advisor professor. I think His contribution is enormous in this community, I believe. Now, Zentropy will also apply to other properties. All right. So if you think about what we have next is that how do we solve the problem, right? What problem do we solve in this one? So one problem is how many of you have heard UMA? No? No? Okay. I said that. So volume temperature. When temperature increase, volume increase. Can volume decrease when temperature increase? Okay. Do you have example? Do you have examples?
Like we can have a gas and
No gas, solid phase.
oh,
Or liquid. Condensed matter. No gas phase. Gas phase is always positive. Temperature increase, volume increase. Yeah.
oh, so this is the opposite.
Yeah, the opposite. The opposite. A temperature increase, a volume decrease. Actually, one of them is so. Sorry.
Water.
Water. That's right. Okay. Water actually is very critical. It's because of this feature, human can survive. Actually, the ocean can survive. Without that one, we'd be big trouble. Okay. The reason because when you kind of freeze, right? All the ice flow out to the top. Okay. So actually that contributes to why the water. Do you know when water becomes negative some expansion, volume decrease with temperature? It's between 4 degrees Celsius. Above 4 degrees Celsius, it goes up. It's only below that temperature. Okay. So that's nature material, right? Yeah. But it's one guy found that you can make materials which do that. Again, it's condensed matter, not avoids anything there. So let's answer that question. Does volume always decrease with the increase of pressure? If pressure increase, will volume always shrink? Can the volume expand with the pressure change? That's an interesting question, right? You should have think about it. Can it go both directions? No, it cannot. Only one direction. So pressure will always decrease when pressure increases. Okay. The reason is because thermodynamics says that pressure and volume go together in the fundamental equation. They have to go same direction, minus P. Minus P increase and when pressure decrease, the volume goes up. Okay. Okay. Now, as we talk about that, the volume will not always increase with temperature. Why? Okay. That problem actually, I believe that we are the only group has the answer for it. Okay. Nobody else has a really good answer. Because most people look at the problem, try to solve what happens in there, right? They didn't look at the system. Okay, you do like the entropy. Right? Okay, UMA was the volume does not increase or even decrease with the increase of temperature, but it only in a certain range. So like the water only below 4 degrees Celsius. But 4.1 degree, no, it can continue to go up. Okay. So this ladder was invented by Swiss scientists. Okay. And he received Nobel Prize in 1920. He was discovered in 1860s, 96. So the thing is that, you probably know that today what's the best in Swiss watch, right? Okay. It actually has something to do with this one. They can control the metals, has zero sum expansion. So mechanically, they stay there. No change. The expansion, you have friction, you'll be trouble, right? Okay. So actually, his invention was all bought by Swiss watches at that time. All right. So this is 100 years later, 1997. It says it's still elusive. But today, if you go to website, still says it's elusive. But I think they should not say it will be solved. All right. So the problem like this. So this is a volume to temperature derivative, right? As some expression. As function of temperature, or another one, which is the simple Einstein pattern, the temperature first goes up, then become zero, negative, then go back again. So of course, I show this one because the line is our prediction on Zentropy. Quantum mechanics, that is no models. No models about how atoms interact with each other, so forth, because that is all taken care of by quantum mechanics. So we can calculate it because you calculate the V to T derivative by the free energy. The second derivative of energy give you some expansion. Okay. So I chose one because if you get a friend right, you can calculate all the properties you can measure. So go back to machine learning. And I'm not a machine learning expert. So people asked me to give a talk at one of the machine learning conference in CMU, was 2018. They said it's great. You have so much data, machine learning about data, right? I give a talk. So I give a talk about machine learning and data because we do machine learning in terms of a traditional one, like you do the Monte Carlo, a Markov chain. Okay, you do the regression. And then I said I need to learn a bit more, right? So I go get understand what really machine learning is. And the professor got Jin-Chao Xu at Penn State. He's a mathematician, and he left Penn State, right? He went to cost, or maybe on leave. So I said, Jin-Chao, give me one course about machine learning. So we went to lunch together at Allen Street Grill, and he was a napkin. So I give this a napkin and talk about all the functions and talk about his. I don't know whether you heard his. He has multigrid.org. That's his one. Multigrid.org. He's one of the famous guys in that domain. Then he said, "Oh, it's so simple, machine learning. It's very simple." I said, "Are you really?" He said, "This one. It's just two functions, linear and activation. Activation exponential, right? That's Boltzmann. So I say you put all the functions together with millions, billions, you solve all the problems in the world." Okay, that's good, right? Linear. Okay, that's okay. So then I had a student, and Dr. Xu and advised my, and his program advised my student. We got machine learning. So the machine learning, this one first, right? The deep neural network. Okay, you have your input, you have output, and this is a paper by Krzyzewski. He's my former student. We developed a neural network to calculate the formation energy. Okay, we learned from DFT data, we created deep neural network. It's one of the best one available. So now it's that if you get structure of atomic position, it will give you the formation energy. Okay? So that's deep neural network. Of course, they say it's pure mathematics, right? There are two functions. They say maybe we should do something else. The physics informed in neural network. Now it's so that means the input output is not just random. They have some physical relations. Okay. So this is the diagram from the Wikipedia. So that means we can constrain our domain of search to some physical relevant stuff. Okay, that's good. So the second one, and then I think that some year later, maybe 1 2 years later, we had a junior faculty, which he's also online here, is Wes Reinhardt. Wes Reinhardt is expert on image design. Okay, so then I learned from him about the generative adversary network. Again, yeah. So again, now you see you have two new networks talk to each other and contrast each other to develop an image design process. Because the dealing is forward, right? Now you get backward. So do excellent work, get publications, get grants and so forth. This year, last year actually, I think Wang Xun's postdoc advisor, Wenrui Hao. Wenrui Hao, he took over Jincao's center. Then we started to talk. He got a great grant to study the Alzheimer's disease. So can you develop a machine learning model for Alzheimer's disease for individual? Big money he do that. Then we talk about how to work on. And then we got a postdoc. And we said we can have postdoc to work on. We have no time, so we get a postdoc there. So we decided to yes.
I have some questions. So this is like metal alloys and here, and that my question is, how is the evaluation and these works thing? I mean, I don't want to.
Yeah. So what happens here is that maybe and Wes, do you want to answer his question?
What was the question?
I want to know, for example, this is a generative model for alloys. How do we evaluate the outcome of such model? Do you run simulation on generated alloys?
Oh,
Yeah.
yeah,
So go
that's a
ahead.
good question. We did some tests where we basically created synthetic data sets and then we tested the GAN performance compared to like high throughput screening or optimization on the like known surrogates basically.
So you have synthetic data to the training, then you have real data to do the comparison.
One other question. What was the size of this data set? As I know, the number of
data points,
alloys in the word is not. Is it that large? Does it work?
I think another student can answer it. Hey, maybe Adam, do you know how many alloy data points we used for this one?
We have the largest alloy data, high entropy alloy data set collected. It's from 560 papers. We have 7,000 property data points, and that corresponds to about 3,000 unique high entropy alloys. I've sent the link in the chat.
Okay, great. So we have this inverse process one when the outcomes would be the origin of it. So the inverse events. All right. So then I started. Maybe then I found something very interesting. I mentioned that two functions, right? You have this linear and exponential. Linear and non-linear, please wait. Linear and non-linear. Then I realized that it's all in my equation. Remember I showed us that statistical mechanics, right? So you see, the blue one is linear. You put the configuration together, linear summation. And then you find that you need the pk log pk, then become non-linear. So each equation has different have non-linear and non-linear. So the entropy, the free energy, and the potential function. Potential function, there is summation of zk. Okay, I don't want to use zk. Zk is my name, right? Zk Liu. But somehow just go together. And then you see the second part you have here. The second part you have here, it becomes exponential, right? And it becomes non-linear activation, basically. Then I thought maybe we should just this include everything in it, right? Okay, so that means now we can think about the baseline. Instead of the deep neural network, we just have the genetic learning, we have the flattened space. Flattened space is all configurations. If you can put all the community together, you can predict the free energy, then you can predict the probability each of them. You can, from the free energy, you can calculate all properties. Because all the properties measure is derivatives of the free energy. First, the second, the third derivatives. Maybe there's some of the fourth one too. Okay? And so what did you learn? So what in our work is that from quantum mechanics, we calculate these values. Then we do the prediction, right? We have shown the case did very well. And but if we cannot calculate, can we just learn from it? So you learn four things. You learn the total energy. You learn the actually difference because ground state can be zero. Okay, just all relative, right? All relative. Remember that difference, right? As all difference. You see, what you have here is the difference. You have the difference. EK, FK is the difference you're measuring, not the absolute value. See if we can learn from this difference. We also temperature because information has temperature. And you have to know how many configurations you have, which you do not know, of course. You can add more and more to that. And then maybe then we calculate properties, right? So let me see if we have a set of data. We can learn this instead of just the PK, we can learn what's behind the PK. Okay? And then you can calculate the properties. That's what you measure. Okay? So that's my Zentropy for AI. Of course, we have a lot of examples. I just give one example. I think Shunwang should do this one. We have all the data on the results, predict results, then we back learn it. Okay, learn what the configuration of DFT values will be calculated. I will connect you with Dr. Shang in my group. Get all the data to learn the configurations. So we have that's the example of iron 3 platform. So what it means that you have the ground state. So this one's the ground state. You have the lowest energy one. You can calculate the energy. Then you can change the spin with magnetic spin. You get a different configurations. These can have different energy. The energy become higher and higher. Higher energy doesn't matter anymore because it's probably zero, very low. The very important information is the temperature and entropy, right? And that was Xunwang is working, Wang is working on, and he created synthetic data with different temperature. Then, if you use the traditional cross the entropy loss function to learn, or use cross the Zentropy loss function to learn, the results are completely different. And what we found is that so far, preliminary results shows that use cross Zentropy learn exactly what you put in. So that's what I have. In our case, you can calculate all the probability from DFT, right? Now to go back to why there's negative supersession. Okay, why volume will decrease? Okay, each configuration volume will increase by temperature. However, when you put them together, the metastable one is going to replace the stable one, right? They'll probably increase. If the new ones itself has smaller volume, the total volume will decrease. That's the fundamentals of negative supersession. Of course, if you study mechanism, that's different, right? There's some dynamics. If you study how the atom change, how the atom change configurations, of course, that's very complex, which is probably not important. All right, that's right. Thank you very much. Any questions? Okay, I think I can.